Hello everyone, welcome back to Learn with Dr. Shobha Nikam. Today we are diving into one of the most fundamental topics for VLSI engineers, semiconductor theory. So if you are preparing for VLSI design, chip fabrication or even device modeling, you can't skip this. So stay tuned till the end and don't forget to like, share and subscribe if you find this video helpful. So before we start with semiconductor theory, let's start from the basics, the structure of an atom. So every atom has nucleus which is made up of protons and neutrons, and electrons revolve around it in shells. So we'll take example of simple silicon. Atomic number of silicon is 14. It means it has 14 protons, 14 neutrons and 14 electrons present in it. And out of those 3, protons and neutrons are present at the center in the nucleus and electrons revolve around it. Now let's say this is a nucleus which has 14 protons and 14 neutrons, and then these 14 electrons will revolve around this nucleus in shells. So see how to decide how many electrons are present in which cell. So there is a simple formula. Number of electrons is equals to 2 in bracket n raised to 2. So n is number of shell. So see, in first shell, if I'll put 1, square of 1 is 1. So number of electrons are 2. In second shell, number of maximum electrons are 2 into 2 raised to 2. That is 4. 2 raised to 2 is 4. 4 into 2 is 8. In third shell, 2 into square of 3. So square of 3 is 9 into 2 is maximum 18 electrons are present in third shell, and so on. But it is not standard. It is not like in every atom electrons will be distributed in this way only. But these are the maximum electrons which can be present in this shell. Here total 14 electrons are present, so they will be distributed as 2 in first shell, 8 in second shell and then 4 in third shell. 8 plus 2 is 10 and remaining are 4. So I'll draw it here. This is my first shell, second and third. In first shell, number of electrons are 2. So 1 and 2 electrons. In second shell, number of electrons are 8. So 1, 2, 3, 4, 5, 6, 7 and 8. And then remaining 4 are here. So this is atomic structure of silicon. It has total 14 electrons, 14 neurons and 14 protons present in it. Here, electrons closer to the nucleus are tightly bound and have low energy, whereas electrons farther away are loosely bound and they have higher energy. So, in semiconductors like silicon, the outermost shell, this is called as valence shell and it has 4 electrons. So these valence electrons play the key role in the conductivity. Now imagine electrons arranged in energy bands. This valence band contains electrons bound to the atom, and the conduction band contains free electrons that can move around and conduct electricity. And between these two bands, there is a gap called the energy gap or forbidden energy gap. For conductors, In case of conductors, this gap is almost zero. Valence band and conduction band, they overlap, and that is why electrons can move freely. Whereas in case of insulators, this gap is very large. So it can be like 5 to 10 electron volt. Whereas for semiconductors, this gap is small. It is about 1.1 electron volt for silicon. It is 1.1 electron volt, and for germanium it is 0.7 electron volt. And 1 electron volt means what? 1 electron volt is equals to 1.6 multiplied by 10 raised to minus 19 joules. So this electron volt is a unit of energy, not voltage. You might wonder, if the band gap is 1.1 electron volt, does that mean we apply 1.1 volts to make electron jump from valence band to conduction band? But not exactly. The 1.1 electron volt is per electron energy requirement. So electron volt is not voltage, it is unit of energy. So this much amount of energy, 1.1 electron volt energy, is required for one electron to jump from valence band into conduction band. And if I'll apply 1 volt across the device, it doesn't guarantee each electron gains 1 electron volt. So if the band gap of silicon is 1.1 electron volt, that means electron needs that much energy to move from valence band to conduction band. Whereas in case of insulator, they need more energy to jump from valence band to conduction band. And this energy can come from heat, it can come from light or an electric field. So in insulators, this energy is very high. In case of conductors, both are overlapping. So that is why semiconductors are special. It is moderate. This band gap energy, this energy gap is moderate, and that is why they are special, and they are not too free like conductors and not too rigid like insulators, but just right for device design, and that is why in chips we use semiconductors. Now let's talk about Fermi level. It is represented as EF. So the Fermi level is the energy at which the probability of finding an electron is 50% at absolute zero temperature. So in conductors, this Fermi level lies inside the conduction band. So even at absolute zero temperature, electrons are free to move. Whereas in insulator, this Fermi energy level lies below the conduction band, deep inside the gap. And in semiconductors, in case of intrinsic semiconductor, intrinsic means they are in pure form. In intrinsic semiconductor, this Fermi level is exactly in the middle of band gap. Whereas in case of doped semiconductors, when we dope group 5 elements or group 3 elements, and when we create 5 electrons in outermost shell or 3 electrons in outermost shell. So in case of N type of semiconductors, this Fermi level shifts closer to conduction band now because one extra electron is present. Whereas in case of P type of semiconductor, it is closer to valence band. I'll show you with diagram. So see here. These are the diagrams for insulators, semiconductors and conductors. Here you can see this is valence band and this is conduction band, and large band gap is present. So large energy is required to move electrons from valence band into conduction band. In conduction band, electrons are ready to move. This and Fermi level is near valence band because during absolute zero temperature, most of the electrons are present near valence band. Whereas these are the semiconductors. So here this is conduction band, which can be either empty or it is partially filled, and this is valence band, and you can see Fermi level is at the center. Whereas in case of conductors, this valence band and this conduction band, they are overlapped. So this is boundary of valence band, this is boundary of conduction band. They are overlapped. So Fermi level is in the conduction band itself. So many electrons are free to move even at zero temperature. So this is Fermi level, where probability of finding electrons in absolute zero temperature is 50%. So in this video, we have discussed about atom structure and electron shells, energy levels and bands, valence and conduction band with energy gap, Fermi level, meaning of electron volt. These basics are very important to understand working of MOSFET, because all chips are made up of MOSFETs and MOSFETs are made up of semiconductor material. So you must know how semiconductor atom looks like, where the electrons are present, what is valence band, what is conduction band, how much energy each electron required to jump from valence band into conduction band so that current will flow through MOSFET. So this is all about basics of semiconductors. Thank you so much for watching, and don't forget to like, share and subscribe. Thank you.